In this problem, we have a spherical shell that we are trying to evaluate the electric field at some point P that is a distance Z above the center of the spherical shell. And just to make sure it's clear that it's a spherical shell, I'm just going to go ahead and just fill it in right here. So this spherical shell we were also given has a surface charge density of sigma. And so what that allows us to do is, since we have a point here situated at the center here, we're able to use spherical symmetry in order to solve this problem. So we'll go ahead and just do a quick rundown on where we're going to just have our little chunk of surface charge density that's going to evaluate one part of the electric field, or contribute to one part of the electric field. I'm just going to go ahead and use a red color right here. So this right here, that is going to be the R prime, which points to the contribution. It can point anywhere around here, right? But we're just going to use it there for the sake of this problem right now, an example. And then from here, from the center of our origin axis, which happens to be the center of our spherical shell, that is going to be our R prime. And so of course the difference between those two are going to be our separation vector, the separation between the chunk at which we are evaluating the electric, the chunk that's contributing the electric field, and then also the point at which we are going to go ahead and evaluate the electric field. So what I'm doing right now is that I'm expanding out that differential size chunk of that's contributing to the electric field. And since we're working with spherical coordinates, and let me go ahead and actually, before I move on to that, let me write, so if we have we're going to transpose this little, this kind of vector here over to here onto our example coordinate axis right here. So if we have that coordinate axis, and this is just an example, it can be completely arbitrary in spherical coordinates, and this is just for orientation. We can go ahead and say that according to the definition of spherical, or our definition for this problem, or spherical coordinates, we're going to go ahead and say that is phi, this is the phi direction, this is the r direction, and this is the theta direction here. And that's going to be important as we move forward, but before I really get into that, we're going to go ahead and just define what this spherical chunk is going to be in terms of our coordinate axes. So this kind of side right here is going to be r sine theta d phi, and this portion right here is going to be r sine, running out of room, r sine, no sine, sorry, r sine d phi right here. Okay, so we're going to go ahead and use that. Oh, I'm sorry, this is theta. So, of course, if you're like me and you're a little bit mixed up on these spherical coordinates, we can go ahead and go back to chapter 1. But right now, since we were given the surface charge density and we're able to find what an example differential surface charge is, we can go ahead and attack some of the substitutions that we're going to make. For example, dq, which is equal to the sigma times dA, some differential size dA, and since our dA was already defined just over here, we can go ahead and say that's the r sine sigma. Let's write that out a little bit neater, maybe not, but r sine squared sine theta d theta d phi. All right, and then finally, as we're already, the whole next point is trying to look at what these vectors are, and this is actually written incorrectly, I'm sorry. This is actually theta hat. We're going to go, since we already did a substitution for the dq, we're now going to look at the separation vector. And it'd be kind of weird if we do it strictly in spherical coordinates, so we're just going to go ahead and do a transformation from spherical to Cartesian coordinates. And if we have some example vector, unit vector r here, that just points somewhere off in our spherical space, we can go ahead and define it as this. And I am pulling this directly from the cover of the inside cover of the textbook. And this is just the definition of a unit vector in spherical coordinates as it's translated into Cartesian coordinates. So if you're a little bit confused on this, again, I recommend going back and reviewing this portion at the chapter 1 at the beginning of the text. This is just the general, the most general sense right here, general form. Now, and we're just going to go ahead and use this as a reference as we move forward in this problem. So the next point is we're going to go ahead and try to define what this separation vector is from here to here. Well, actually, I kind of drew that a little bit incorrectly. Let me go ahead and fix that up real quick. So that would be from here to here would be our separation vector. Anyways, so we'll go ahead and just define what we can. Going back from kind of the first principles, we know the separation vector is the distance or the difference between those two. So we're going to go ahead and just define this r vector, which is the point from the center of our coordinate axis all the way up to the point that we have here. And so if we go ahead and translate that over to our example coordinate axis right here, we can tell that it's only in the z component, and then it has some magnitude of z, right? So we're just, as you can see, we're going back and forth, transposing spherical onto Cartesian coordinates, but Cartesian coordinates is going to allow us to make the math a little bit easier, as you'll see in a second. So now so we already attacked this vector right here, so now we're going to attack this arbitrary vector right here. So of course, in the most arbitrary sense, some vector that just points off into space is just this chunk right here. But one thing that we do notice and we do have on our side in terms of the given is that all these r's that we have right here, since this is a spherical shell, it's going to, every contributing chunk of the spherical shell of the surface charge is only going to be at the extent of the radius. So those are only going to be r. So we can replace the little r with the constant big R. However, all of our other variables such as phi and theta will stay the same, but that's okay. I'll go ahead and write those now. Okay, this is great. As you can already tell, we have two z components that we're going to have to combine, but before we do that, I'm going to go ahead and just define our unit separation vector, which is, we're just defining in the most arbitrary sense what is the direction of that separation vector, not necessarily the magnitude. So we're going to have to normalize this thing by its magnitude. So the way we're going to do that is, first of all, we'll just combine these two z coordinates. I'll put those last, actually. So the first thing I'll do is, so we have some sort of negative x hat component. And what I'm doing is I'm just substituting all this chunk of stuff into these dots right here. And you'll see why in a second. Usually whenever I do that, it generally means that they're going to be canceled out or going to zero. They won't eventually matter. And that's going to be very apparent in a second. So let's see here. It's r, let's make that a little bit neater. R cosine theta in the z hat direction. And this is all divided by the magnitude of that separation vector. And the weird part is, and this is what was hinted at in the text of the problem, is that if we were trying to find the magnitude of this big chunk of stuff right here, then that's going to be a little bit harder. But what we can do is utilize the law of cosines to find that out. So what I'm going to do is I'm going to take this unit vector right here, and I'm just going to move it down right here, or the separation, the whole triangle thing that we got going on here. So if this is our z, actually, let me move it down a little bit more. So if that's our z, I should go ahead and write that now. So that's our z. This is the point, and this is the center of our origin. This is some arbitrary triangle, essentially. See, this is our r magnitude of the r prime right here. And this is the magnitude of our r vector right here. What we can do, and since if we use this, since this is pointing off in this direction, and this sweeping angle from the z all the way down to wherever our hat is pointing is our theta, right? And so we can do the same thing down here. So this is going to be our theta if we transpose that, right? So now what we can do, is hinted at in the problem, is use what's called of course the law of cosines in order to find this out, where the magnitude of r is equal to the r squared one side plus the squared of the other side minus twice the product of those two times the cosine of theta, all under, this is going to look kind of weird, but all under the square root, right? This is all multiplied by each other. So we can go ahead and use that into our denominator for the magnitude of r squared, which we'll do that right now. And this is all under the square root. There we go. So now what we've done is we went ahead and just found our two last pieces of the puzzle. We have our magnitude, or sorry, our unit vector right here, and we also have the magnitude of it right here. That's we just go ahead and divide. So we'll go ahead and put those in. So I'm just going to go ahead and write a note equals, just to save time. If this was like my homework problem, I would have explicitly wrote this down just so I could follow closely. What I like to do my homework problems is be able to have that and just kind of reference that over there, but this ends up being like my main chunk of logic flow. So let's go ahead and just take all these and throw them in there. I'm going to write the equal sign over here because there's going to be a lot of, I think it's going to be expanded out a little bit more. So already, before I even do this, I can tell this is going to be a double integral because looking right here, we have our two limits. So the first limit is going to be theta, and theta sweeps from 0 all the way to pi. So we'll go ahead and put that right now. And then finally, phi sweeps from 0 to 2 pi. And next, I'm just going to go ahead and just explicitly do our separation vector, unit vector. And on the z-hat direction. And like I said, this is gonna get crowded. Might have to move this over, but that's okay. Luckily, we're working in digital form. Okay, so normally this would be in the square root, but the next portion that we're going to do is do the r squared, and since the r squared is the same as this will end up being over to the 3/2, so I'll just go ahead and write that down to save us some time and some space. Both of those things are really good things to have. And speaking of space, let's go ahead and move this over a little bit because we still have the differentials to put in here. And you know what? Instead of actually doing that, I'm going to put the differentials right here on top of this one. Not the differentials, I'm sorry, but the constants. So the sigma and the r squared are all constants as the integral sees them. And then finally, I'll do the sine, quantity of sine theta d theta d phi. Okay. Now, what we're going to do is, the main thing that we're going to look at is some symmetry, of course. So if we look back over here, if we have our origin and we're evaluating the electric field at that point, let's say we have that chunk that's right here, right? And that produces an electric field, which of course has some sort of component this way and some sort of component this way. Exactly opposite of that is another point that's equidistant from here, and so they all have they both have contributing parts in the z-hat direction. However, they have equal and opposite magnitudes or directions in the x-hat direction. And the same goes if we were able to spin this thing a little bit, we would also be able to see that from the y-hat direction. There would be two contributing portions that cancel out for the y-hat component. So as we can tell from symmetry, of course, thanks to this perfectly spherical shell, we can go ahead and get rid of all the x and the y-hat components. So I'll go ahead and just explicitly write that now. I'll just write little x's over there. And all that's going to be left is the z-hat component. So in an effort to clean things up, I'm just going to go ahead and write that out explicitly right now. Double integral x. And then we have our magnitude, courtesy of the law of cosines. Law of cosines is one of those things where it's just such a great tool, but for me at least, I always seem to forget it, that it's available. Like that it's in the inventory of tricks that I can pull out. And it's really nice that the author was able to remind us about that. Okay, so we did a good amount of physics right now. And the next thing that we're gonna do is we'll go ahead and look at this this phi integral here. So this phi integral, there's no phi's that are inside here, so that's the easiest thing that we can go ahead and evaluate, which we just tack on a 2 pi. So I'll put the 2 pi out here. Actually, I'm going to put the sigma, and then I'll put the 2 pi r squared. You might be able to tell where I'm going with this, and the fact that I'm not going to actually cancel anything out within the 2 pi right here. That's going to be useful later on whenever we interpret our results from this problem. Usually I'd like to cancel things out as we go because it helps prevent things from being a little bit too complicated, but these problems where we're working in spherical coordinates and you see a 2 pi r squared pop out, and I'll make it squared a little bit more explicit, you might be able to keep those in your pocket because you know that might be useful later on. Okay, so I'm going to scroll up a little bit here because we've got a lot of work to do. So there's this nasty looking integral, including this sign right here. So an important thing to note is, you can do this integral using U substitution, which is totally fine. However, I personally enjoy using the integral tables for this kind of stuff, these kind of things. And so if you use the integral for these things and for an effort of time, as you can see that the result of this is these two actually end up switching right here. And so it's r minus z cosine of whatever was the limit that we're evaluating at. So this time it's actually pi divided by the square root of what's all underneath there. And this family, you're going to be really used to working with the family of integrals where it's, something divided by the 3/2 of something else in the denominator. So this is going to be pi here, and this is all going to be under square root. All right, so that's the first one. There's also z squared that's in this, but it's going to be common to both of these limits, so I went ahead and just pulled it out right here. So that's minus, of course, the other side of that coin, which is cosine of 0, which is the other limit that we're evaluating the integral at, divided by almost the same thing, 2rz cosine, oh boy, of 0. Let's just say that's underneath there. All under the z hat direction still. Okay, so we'll go ahead and evaluate these things. So cosine of pi is -1. Cosine of 0 is +1. All right, so let's go ahead and write this out. And I put this quotation marks because, unlike the ... dots, they do matter. It's just for the interest of time, I'm just carrying these straight down through here. 1 over z squared. Okay, so what we have is r plus z right here, square root of squared plus z squared minus plus 2rz minus the difference between the two, and then r squared plus z squared minus the difference, or the twice the product of those two, all under the z hat. Oops, z hat. Okay. Now, I'll go ahead and explicitly write this out since we're losing it up top. Okay. So what we have here is we have a fork in the road, right? And it was kind of hinted at in the And the problem too is that this integral, or this square root right here, oh boy, this square root right here is a fork in the road. We have two possible answers depending on what the value of z is, right? And we need to evaluate both. So if r is less than z, so if that point, let me go ahead and write it out right now. If we have that circle, which is much more symmetric than that, or that, there we go. Okay, we're gonna call that a perfectly symmetric circle. If this is r right here, and then our point is further than r, so okay, that point is outside of the circle, then the positive square root of that is going to be z minus r, right there. But if our point is inside the circle, so if we're evaluating the electric field within that spherical shell, then that means that r is going to be greater than 0, and the answer to that square root is going to be r minus z. The positive of that square root is going to be r minus z, all right? So I'm going to go ahead and scroll up here and get a little bit too ahead of myself, so I'll go ahead and bump this down right now. So we're going to just go ahead and evaluate the case for r is greater than z right now. R is greater than z. All right, for this case, we're going to go ahead and explicitly write this one out and evaluate. So this one is going to be r plus z. Regardless, this will be r plus z minus the difference between these two divided by, and then just like what we set up here, in this case, it's going to be r minus z. So we have r minus z, all in the z hat direction. My brackets are not the same, but that's okay. So again, so this is the point that's on the inside. And one of the things that we might be able to see here before we even start attacking this problem right here is to try to get an idea of what we think might happen. So if we have a point, again, assuming that the circle is symmetric, is that if we evaluate the electric field right here, we're going to have some contributions from each side as we keep going on and on and on, right? And what we'll see is that these components, the horizontal components right here, are going to cancel out, and we're going to be left with the z component. But then there's a threshold right there where they're actually pushing in this direction here. So the vectors look smaller, but that means the electric field gets stronger because that point gets closer to these charges. So we know we're going to get some sort of weird canceling out, but without actually doing anything math or a whole lot of actual understanding of what's going on, we understand that there's going to be an interesting amount of canceling out that's going to happen, but nothing glaring that'll say like, hey, this is exactly going to be the answer. So we do have an idea of where we're going to go down. So moving on back to the math is that we're just going to look at this and get them under the same denominator, so that denominator being the product of the two. So I'll go ahead and write it out, r plus z times the quantity of r minus z. And then here we have r plus z, r minus z, the product of the two, r minus z. Z hat direction, immediately what you'll see is there's the answer. All this stuff cancels out to 0, so no matter where we put this z inside the a perfectly symmetric, unlike what's shown here, a spherical shell, the electric field inside the spherical shell is going to be 0 no matter where we put it. And that's assuming it's a uniform density and perfectly spherical and all that stuff. So that's a really important result that we're going to use over and over and over again, pretty much through this entire textbook. So make sure to keep that in your pocket and be able to use it for later on, because it's, like I said, it's going to be really, really useful. So that's for that portion. But what if z is on the outside? What if we have our perfectly spherical shell, which I drew right there, and it's actually the point z, point P, a distance z from the center is actually outside, then our spherical shell is going to look different. So I'm just going to go ahead and copy and paste this down here and accept our the answer to our square root, as I set up here, is going to be, oops, I actually said that. The answer is actually going to be z minus r in this case, z minus r in this case. So if we go ahead and do that, so remember z minus r, if we do some math and stuff like that and switch it around, we can go ahead and say that the, did I write that wrong? Z minus r. Yeah, for z minus r. Sorry, just getting a lot of math going on. I'm a little tripped up. So we'll go ahead and put that down there. So that's the main change I did. That would be the positive square root of our square root that we have right here. So scrolling back down to here, if we go ahead and evaluate this and put it under the same denominator, we'll see that let's see here. We'll see that the answer here is going to require a little bit more math, but we're almost there. So z minus r, same common denominator, r plus z minus r minus z, and then r plus z. Still pointing in the z hat direction. What we'll do is keep this as a glob of constants. And then we'll go ahead and pull a z plus r out of all this. I'm sure there is probably a different route you could have taken in terms of the math for all this, but I'm just trying to make it a little bit more explicit for everybody. So z plus r, you can see where this is probably going already. And if that's so, that's good. Now I'll go ahead and explicitly write the constants out front, since it looks like we're about to lose them, just like how I lost the 1 over z squared. The 1 over z squared from up here. Apologize for that, but that's okay. So what we go ahead and do is cancel out that 1 plus, the r plus z, and all that's going to be left is a 2 times z minus r, then the z minus r here. Convenient again, cancel that out. All that's left now is a 2, so we'll go ahead and bring that 2, and this is the whole reason why I left that, that 2 out in front. So now this 2 becomes a 4 pi r squared, hint, hint. 1 over z squared in the z hat direction. So as you can tell, what's happening right here is that is actually equal to q, right? Oops, sorry, that's actually equal to a. And when a is multiplied by sigma, this is all equal to 1 over 4 pi epsilon naught q divided by z squared, putting the z hat direction. So if I can bring this down a little bit, what just happened was we were able to look at this spherical shell, and if we were able to think about what this actually represents, this actually represents if we're able just to collapse this spherical shell that has a surface charge density of sigma spread out across some area A, is if we were able to collapse this down to a single point and treat it like a single point, it would actually feel like a point charge with some charge of Q that is acting on this point charge here. So as long as we have spherical symmetry, or some sort of symmetry here, and we have a uniform charge density, the electric field at some point P, if we just completely just look at the point, it's the same as if we just put a point charge here as if we had this spherical shell, no matter where we put this P, again, with all the assumptions that I just said there. And that's a really interesting point, and just like how I said with if that point was on the middle where the electric field is equal to Z, we're going to use that over and over again within electrodynamics and electrostatics. So again, it's important to keep this tool in the back of your pocket and use it as we move forward.